Okay, welcome back everyone to Emily's third lecture on of the HoTTEST summer school in 2022. Today Emily is gonna talk about function extensionality and all the things that you can do with that.
Great. Thanks so much. It's really been a pleasure to be here, and I'm particularly looking forward to today because we can finally prove a bunch of things that, or answer a bunch of questions that I think we've been delaying, and I'll try and explain why. So first, there are lecture notes for today that are on the GitHub. If one of the TAs could drop that link into the chat, that would be awesome, just the direct link to the lecture notes, but for the folks watching later, you can find it on the resources for the summer school. So I want to start by asking the following question. So let's let A, B, and C be types. So what I want to illustrate is the sort of question that it would have been natural to ask like a month ago, but we haven't yet answered. And then I want to explain why we haven't answered that yet. So a very natural question is, what is the relationship between the following types? The relationship between. So on the one hand, we could think about the type of functions out of the product of A and B and into C. So that's a type. Or we could think about the type of functions from A to the type of functions from B to C. So remember, the second type has an implicit parenthesis here, though it's not common to write it. So I'll get rid of that. So what are the relationship between these types? So classically, if we were talking about set theory, the left-hand thing is the set of functions out of a product. So, and the right hand is a set of functions out of one set into the set of functions out of another set into C. And there's a well-known correspondence between these two collections of functions called currying and uncurrying. So it would be natural to ask whether we have the same thing in type theory from the rules that we've given. So it's not so hard to define comparisons between these types. So we can exhibit a logical equivalence, meaning I can define a function that will take as input a term of this left-hand type and give as output a term of this right-hand type. So how does this function work? So it would take, I'll say defined by, so it would take a G, which is a term of this type, then pick up an A, which is a term of type A, and a B, which is a term of type B, and then I need a term of type C, but I can just get that by evaluating my function G at the pair AB. So I'm going to call this function evaluate at a pair. And the thing I want you to note is this definition. So the definition of the function ev pair uses the introduction rule for product types. Uses the introduction rule for product types, which in particular supplies a function that given a term of type A and a term of type B provides a term in the product type. So we often write this function in this way. This is the pairing function. And that was used here. You can understand this ev pair as like a precomposition with this pairing function. A function G in this type of functions from A times B into C would be defined on an arbitrary term of type A times B, but certain terms are pairs. So we could in particular evaluate the function G at a pair. So that's the map in this direction. So for a logical equivalence, we also require a map in the other direction. So that would take a term of this function type and produce a function out of the pair type. This comes from the induction principle for product types, from the induction principle for product types. So let me recall that, or sorry, let me say let me say the elimination rule. I'm using a synonym deliberately just to review these terms. The elimination rule for product types. So product types are an instance of these inductive types. So which gives the following induction principle, following map. So for any, I'm going to call this the general form of this induction principle for product types. So for any family of types that depends on two terms, one of type A, one of type B. So this is a P XY, or actually, sorry, let me phrase it. Let me phrase it this way: for any family that depends on the product type. So this is a family of types over the product type. So the induction principle will allow us to construct a dependent function, so a section of this type family, from the data of a function that takes a dependent function that takes an A, a B, and B, and then provides a term in this type. So informally, this induction principle says that to map out of the product type, it suffices to consider the special case where my term in the product type is a pair. So this is this function ind times, and the other direction of the logical equivalence is really just this function, but in the case where C does not depend on A and B. So I mean, here C is just the type that is independent of A and B, but we could consider it as a type family over this product just by weakening by a constant type family. And then this induction map specializes exactly to what we want. Okay, so what have we done? We've exhibited a logical equivalence between this left-hand type and this right-hand type, but we might expect that these types are genuinely equivalent. So that's the next question. Can we promote this to a genuine equivalence? This to an equivalence. So in order to do so, what we require are a pair of homotopies. So let's just try and construct them. So on the one hand, this requires homotopies. So if these types are in fact equivalent, then there must exist the following homotopies. So one would be a homotopy between the composite of ev pair with this ind times and the identity function. So what is a homotopy? So in other words, for each term in the domain of this ind times function, so for each function f from A to B to C, we need, so to construct this homotopy, we need an identification. So remember, these types of homotopies are product types. So for each f of this form, I require an identification. So f is a term inside this type, and I would need an identification between a pair of ind x of f and f. So let's see if we can define that. So, well, what can we say about this? So for each pair of terms, so for any A in A and B in B, we have some definitional equalities. We have definitional qualities. So what I'm about to do is I'm about to unpack the definitions. So ev pair of ind x of f is the name of a function. I could evaluate that function at an A and a B. And when I do so, so this ev pair of this function just is the function that would evaluate a pair. So this is definitionally equal to, let me use this symbol, which appears in Egbert's book for definitional equality. So this is definitionally equal to the value of ind x f at AB. So ind x f is a term in this type. So it's a function that takes in an arbitrary term of a product type and returns a term of type C. But the way by the computation rules for index, this is equal to f of AB. So in other words, where this last definitional equality, this last definitional, just to emphasize, equality is the computation rule for the product type. As the computation rule for the product type. So it says that if you use the induction principle, this is just generally true for inductive types. If you use the induction principle to define a function by the special case on pairs, then when you evaluate that function at a pair, you recover the original term that you had initially. So that's the second definitional equality. But then by the eta rule for function types, so let's apply it first to f, which is our term from our function from a to b to c. It says that f, so that's a term in this function type, is definitionally equal to lambda a dot lambda b dot f AB. So this is something called the eta rule. The beta rule compares the lambda abstraction and evaluation in the other order. The eta rule is this particular one. And moreover, this definitional equality, but by above we calculated. So this was the calculation that involved the computation rule for product types. We calculated that if we look at the function ev pair of ind times of f at a b, we have the same value of fab. So again, by this eta rule, we have that ev pair ind times f is equal to lambda a lambda b f ab. And so therefore, thus, we can use Riehl as an inhabitant of the type that we wanted. We were looking for an identification. So that we were looking for a term in this type. And in fact, by all of the computation rules, so both for product types and for function types, we have Riehl in here. And this gives the homotopy that we want. So this gives the homotopy. So what we've, sorry, which homotopy? It's the one that says that ev pair composed ind x is homotopic to the identity. So we've shown so far that this induction map is a section of the evaluation map. So we're close. So the final step is a homotopy in the other direction. So the final step in the proof of the equivalence requires a homotopy in the other direction. So we need to consider the composite of this induction map with the evaluation map and prove a homotopy there. So we require identifications. So what is a homotopy? It means for all terms in the domain of this thing, you need an identification. Identifications for all. And now we're going to consider term G of type A times B to C, because that's the domain of the ev pair map. So we need an identification between ind x of ev pair of G and G as terms of this type. So, and here we have, so by definition, this ind x of ev pair of G. So ev pair of G, sorry, this ind x, ev pair of G was the function lambda A, lambda B, G, A, B. So once more, so for terms A and B and B, we have, so we can compute this left-hand side again. So the induction of the evaluation at the pair at G. So this is the name of a function. I could apply it in particular to a pair. And once more, this is just definitionally equal to the value of G at AB. So in other words, as before, REFL, or maybe more precisely, sort of lambda A dot lambda B dot REFL is an inhabitant of the type that takes an A and a B and a B, and produces an identification between this induction of this evaluation pair G at AB and GAB. So here I'm using the identity type, but I can, because I have a definitional equality, then that gives me a term in the identity type. Okay, so this is not quite what we need. So using again the induction principle for product types, we can promote this. And what I mean is the type that we've inhabited, I'll just copy it here, is not quite, does not quite capture the full domain of the type G, but I can promote it to a identification involving an arbitrary pair. So I could think about the induction applied to of pair G evaluated at an arbitrary term in the product type. And I can identify that with G of P because I have, so again, this induction principle for product types can be used to construct sections of arbitrary families of types over the product type. So that's what I've done here. So in other words, if I apply this induction principle again, but now meant in this particular case for this more complicated type family. So if I apply that to the term lambda A dot lambda B dot REFL, which was my inhabitant of this left-hand type, I get an inhabitant of this right-hand type. So this is for all P, I have a map, an identification between index of pair of G of P and G of P. And so what have I done? I've constructed, so this type here is the type of homotopies from the induction of pair G and G. So G again was a function from A times B to C. So this is just the type of homotopy. So what I've constructed here is a homotopy, A lambda B dot REFL. But that wasn't actually the goal. So remember my goal, I am trying to construct a homotopy, but the sort of homotopy that I'm trying to construct is this homotopy between evaluation followed by the induction map. And for that, I require an identification. So I need an identification between this function and this function, both terms of this function type. What I've constructed instead is a homotopy between these two functions, which are terms of the function type. And we're stuck here. We're stuck here because we do not have a way, because we cannot, in general, turn a homotopy, cannot turn this homotopy into an identification between the functions, into an identification. So the type that we were trying to inhabit was this identity type between this function from A times B to C and this function by A times B to C. And a homotopy is just not quite good enough. And that's what today's today's lecture is about. So the function extensionality axiom is what I'm about to introduce. The function extensionality axiom characterizes identity types of function types. Identity.
Emily, quick question. Let's
Yes.
suppose that if instead of defining one of the converse maps using the induction principle, we instead use the projections. and we had ADA laws for that element of the pair is definitionally equal to the pairing of its projections. Would this get around the issue in this example?
So there's in an example we're going to give later about the type theoretic axiom of choice, I think an ADA law for a pair type would solve that one. I'm not sure. Right. I guess, sure. I guess that would work here as well. If we knew that every term in the product type was definitionally equal to a pair, then we would be fine using the ADA rule for function types as well.
And really, we'd have that for records, but not for the inductive type.
Okay, so that's a level of subtlety that's beyond me, but great. But yeah, if you can play around with this in AGDA, and in fact, I did before while preparing this lecture to make sure I wasn't lying to you. So if you define the product type as a data type, it will not accept REFL here. But maybe records and data types are different in a subtle way that I don't quite understand. So yeah, so I mean, this is quite a subtle thing, but maybe the example, yeah, I wanted to give a very concrete example of the, sort of why we haven't been claiming equivalences like this all along. But I mean, the real point, the sort of meta point is that, we don't, without characterizing an identity type of a particular type, so in this case, we're interested in function types, we don't in general have very many ways to construct terms of that identity type. I mean, the rules for the Martin-Liff identity type give us reflexivity, so these sort of trivial identifications, and that's it. We have no general way to construct any non-trivial identifications until we have some sort of characterization of the identity type family. So whether or not this particular example is motivating, maybe that should be motivating in general. If you have two terms of a function type that are not trivially equal, but ought to be identifiable in some sense, we really like some strategy for that. And it would be natural to regard a homotopy between functions as some identification of sorts. That's kind of an idea that we've been using all along in our use of homotopies in various definitions. It's an idea that would be very natural to algebraic topologists, and the function extensionality axiom will provide that for us. So let me state function extensionality now, but that was a great question, so thanks, Astra. Okay, so what is function extensionality? So function extensionality. So maybe it's natural to ask, why don't we yet have a characterization of identity types, of function types? We have characterizations of identity types and lots of types of, coproducts and the natural numbers and the Booleans and the unit type and dependent pair types. Why not also dependent function types? What distinguishes the dependent function type from all of the type families that we've just mentioned? Any ideas? Yeah, so there's a suggestion in the chat that it's more primitive. That's certainly true in the proof assistance. I guess I don't know. I mean, I think it probably is more primitive. I'm happy to accept that. But there's also a general name for the type of types that we, the collection of types that I've just mentioned, the product types and the sigma types and the coproduct types and the unit type and the natural number types are all inductive types, absolutely. And this function types are not inductive types. And we use the induction principle to prove the characterizations of the identity types in those other cases. That proof strategy is not available here. So what function extensionality is, so firstly, so this characterizes identity types of function types, characterizes identity types of function types. It provides this thing that is missing, types of function types. And the other thing to say about it, and the reason that it's been delayed so long, it's an axiom. it's an axiom that we will now add. So from this point on, that we will add to Martin-Liff type theory. So this is not something that's provable from the other axioms that we've stated so far in type theory, though we will add it now. It will be provable from the univalence axiom that we will add later on. So ultimately, we would just require one additional axiom, not two. But let's do this one first. Okay, so there are several equivalent ways to state the function extensionality axiom, and so let's start there. So this is a proposition giving our preliminary statements of function extensionality, and it says for a family of types, so for a type family B over A, the following are logically equivalent: B A to U, the following are logically equivalent. And so these will all give equivalent ways to understand this functionality axiom. So the first is perhaps the most traditional statement of it. So it says, so the family of maps, so this map will say for any pair of dependent functions. So given my type family B over A, I could consider a pair of dependent functions, and I could consider an identification between them, or I could consider the type of homotopies between them. And there's a canonical map in this direction that turns an identification into a homotopy defined by, so by path induction, it suffices to give an image of the reflexivity term. And there's a reflexivity homotopy that we've encountered on various occasions. And if you don't recall it, it's a good exercise to remind yourself now. By path induction, this defines this map, which we're called homotopy ID. And the first statement of function extensionality is that this map is a family of equivalences. Family of equivalences. So informally, what function extensionality is asserting is an equivalence between the identity type for a pair of functions and the type of homotopies between those functions. Okay, so what's statement two? So statement two is that for any dependent function, so now I'm going to fix one of these dependent functions and then consider the type where I'm going to take the sum over an arbitrary second dependent function and the data of a homotopy between F and G. And the second statement is that this type is contractible onto the term that we know about. So onto meaning with a particular center of contraction, this term F, and then this Riehl homotopy at F. So we certainly know that this term inhabits this sigma type, and I'm asserting that the type is contractible. So that's the unique term in homotopy type theoretic sense. And then the final statement is a little bit more abstract, but we could say the principle of homotopy induction holds. Principle of homotopy induction holds. So it says for any family of types P, any P, depending on, say, two dependent functions and a homotopy between them, the evaluation map and this is going to be evaluation at the reflexive homotopy. So it would take, so its domain is, again, a dependent function type, which is going to be a bit of a mess to write, unfortunately. P, F, X, H. So this is constructing a section of this entire type family. So I could map from here to the smaller dependent function type that would just give a section in the special case where I'm evaluating P at F, and this Riehl homotopy. And the statement of this principle of homotopy induction is that this map has a section. Okay, so what this theorem states, there are three different logically equivalent ways to understand the statement that the identity types and dependent function types are equivalent to the type of homotopies between the dependent functions. And this is just a special case of a more general result that we've seen in the past. So this is a specialization of the universal property of identity types. Of the universal, and this is identity types in any type family. So in particular in dependent function types, which is the case we care about right now. Property of identity types. So you might remember that that theorem characterized what was called there an identity system. So another dependent type family that is playing the role of the identity type family up to equivalence. And there was a characterization saying something or other is a family of equivalences, some total space is contractible, and then some induction principle holds. And this is, we just have to translate that result to this special case. Okay, so what's more interesting and also I think more useful is a fourth equivalent characterization of function extensionality that's more surprising. So this is the one that you really need to know and I think is the most interesting. So there is a fourth equivalent characterization. So this is used kind of all the time in proving things, and also it's just a little bit more surprising that it connects to function extensionality. I believe this is due to Vygotsky. Maybe someone will correct me if that's wrong. And firstly, there's something that's a little bit interesting about the statement. So for any universe U, the following are logically equivalent. Logically equivalent. So the first thing is that the function extensionality principle, as we've defined it above, holds in U, but I'll state it again just as we get used to it. So the function, sorry, my handwriting today is atrocious, but this will help you learn. Function extensionality principle holds in U, and what that means from the point of view of the universe is that for any type family, so A is a type in the universe and B is a type family valued in that universe, the map, which we defined above by sending Riehl to Riehl homotopy. So this takes dependent functions and an identification between them to a homotopy between them. So this map is a family of equivalence. So meaning again, for each particular F and G, I have an equivalence, family of equivalences. So that's just the statement of functionality repeated again as we try and internalize it. And then statement 2 is where the excitement comes. So this is something called the weak function extensionality principle holds. The weak function extensionality principle holds. And what is that? So it says for any type family, so as before, so for any B from A to U, on the one hand, we could consider the hypothesis that for all X in A, the fiber over X is contractible. So B of X is contractible. So that's an assertion. And what weak function extensionality says is that it follows that the entire dependent function type is contractible. So another way to state weak functionality, or sorry, weak function extensionality is that products of contractible types are contractible. Products here are meant in the sense of these dependent products or dependent function types. So if for all x and a, the type b of x is contractible, then when I product them all together, when I form the dependent function type, functions from a into b of x, that whole type is contractible. So, right, what's interesting here again is, so once I've proven the logical equivalence between these two statements, if you believe me when I said that it's not possible to prove function extensionality from the other axioms of type theory, it will follow that it's not possible to prove weak function extensionality either. And that's also a little bit interesting to think about. So that's something I invite you to explore on your own time. Okay, so I'm going to prove the logical equivalence between these two. This involves ideas that we have not seen yet. So I'll give the full proof. So let's assume one. So I'm assuming function extensionality, and I'd like to conclude weak function extensionality. So my goal is to prove this implication in two. So I'm going to assume one, and I'm going to consider then a type family B over A. And suppose that for all terms x and a, b of x is contractible. And we're going to use the proof of this. We're going to use the data involved in a proof of contractibility. So let me give names for it. So with so cx in bx as the center of contraction, and in the notes I use the capital letter, but I think my handwriting is not quite good enough for that. So let me use hx as the contracting homotopy. So what is a contracting homotopy again? It would be a map that for all, I don't know, y in bx gives a map from c of x to y. So that's my contracting homotopy as contracting homotopy. Okay, so my goal is to construct proof that this dependent product type is contractible. So I need, again, a center of contraction and a contracting homotopy. And I'm going to define C to be the function lambda x dot c of x. So this is a term of type x and a, b of x to be the center of contraction. Again, my goal is to show that this type is contractible. So I need a point that it contracts onto of contraction. So I need a contracting homotopy. I need a homotopy. So what the contracting homotopy would look like is for all f from, so terms in this type, I would need an identification between my C, which I've just defined, and F. But by the function extensionality principle, by funx, so funx is the traditional abbreviation for function extensionality, and I think I'll start using it now. It suffices, rather than defining an identification between the function C and the function F, to give a homotopy, give a term of type C homotopic to F. So to get this identification, that's all I need to do is get a homotopy. That's what the inverse equivalence to this function extensionality axiom provides. This again is the type that for all x in A gives an identification between C of x and F of x. But I have this, this is given by lambda x dot h of, I guess, h of x at f of x. So that's going to be a term that gives a homotopy between C and F. And that's typically how function extensionality is used. It reduces, it reduces identifications between functions to pointwise identifications between functions, which is often easier data to come by. Okay, So now let's do the converse. So that was the proof that function extensionality implies weak function extensionality. And now we need to go the other way. So I'm going to assume 2. So this is, I'm assuming, so the statement of weak function extensionality that was that contractible types are closed under products. So I want to prove now ordinary function extensionality. So an equivalence between identity types and function types and types of homotopies. So by my first proposition that gave 3 logically equivalent characterizations of the function extensionality axiom, it would suffice to show that some total space is contractible. So let's do that instead. So my goal is to show that this type here is contractible. So we must show that this type is contractible. And to do so, I'm going to relate it to some other type. So consider so I'm getting a little bit ahead of myself, but I'm going to call this a section retraction pair. So I'm going to define maps relating this sigma type. So we'll start with this over here. And then I'm going to relate it to the type where I take the product. So for all x and a, and then I take a sum over the fiber y in b of x. And then I'm going to look at an identification between f of x and y. So this map I'm going to call S, and this map I'm going to call R, and it's going to land back in the type that we're trying to show is contractible. So where I need to define these maps for you. So S is defined to be the function that, so by sigma induction, it would suffice to define it on a pair. So I can take a pair. So G is my dependent function, H is my homotopy. And given that data, I can inhabit this function type. So that's, I take a lambda x, x is my term of type A, by pairing together just G of x and H of x. So that's this map S and the map R. So I'm going to let P be the name of a term of this dependent function type. And now I'd like to inhabit this sigma type. So I'll inhabit it via a pair. And the bottom term in the pair is a term of this dependent function type. So I need a lambda x. And then I'm just going to take the first component of my P of x. So x is a term here. P of x is a term of this pair type. If I project to the first component, I can define that. And the second component is lambda x dot PR2 P of x. So P of x is the data of a pair, and I'm separating out the 2 projections. So that's this S and this R. Okay, so this composite in the direction that I've indicated, R composed S, is homotopic to the identity function, homotopic to the identity by the computation rules for sigma types and pi types, rules for sigma and pi types. So this is very similar to the sort of argument that we gave in the introduction. So I won't say anything more about that, but it follows similarly. You can just directly construct this homotopy, and it'll be inhabited ultimately by reflexivity by using these computation rules. But what have we done? But the type in the middle type is a product of a family of contractible types. The middle type is a product of a family of contractible types, family of contractible types. So in here, I have, this is the based path space for the term f of x of type b of x. And that's, we've seen many, many times, that's a contractible type. So by weak function extensionality, this whole product is contractible. So by weak fun x, this middle type is contractible. The product is, it's also contractible. And a thing that you've seen on your homework is that if you have what's called a retract of a contractible type, then your type is itself contractible. So since contractible types are closed under retracts, or since retracts of contractible types are contractible, we're done. Retracts of contractible types are contractible, we're done. So good. Okay, so what we have seen so far is function extensionality is this axiom that says that up to equivalence, identity types and function types are equivalent to the homotopy types, the corresponding types of homotopies. And what we get to do today is just prove myriad consequences of this axiom. So the rest of today will be consequences of function extensionality. Today will be applications. And many of the applications will be applications of this full function extensionality principle, but some of them will also be direct applications of weak function extensionality, and that includes, well, actually both of those statements will be included in this first result. So the first set, so, and I'm going to have that as an assumption from now on. So we're asserting function extensionality and seeing what we can prove from it. And the first consequence is as follows. So for any type family, B over A. So what weak function extensionality asserted is that if I take the product over X in A, and then asserted that the fibers were contractible, then the entire product is contractible. And what we'll do now is extend that to the higher truncation levels. So you might remember contractible types are the -2 truncated types. They're the base of some hierarchy. And this is the corresponding result for the higher truncation level. So what we're asserting is that propositions, that was the -1 types, are closed under products, as are sets, as are 1 types, as are 2 types, etc., for all truncation levels. Okay, so everything that we know about truncation levels we proved by induction on the level, and this is no exception. So the base case where k equals -2 is the weak function extensionality, is weak fun x. Since we're assuming fun x, we have weak fun x as well, and so that just holds. So for the inductive step, we get to assume that products of k types are k types, that products of families of k types is the way to say k truncated, families of k types are k types. And we want to show that if B is a family and for all x in A, B of x is a k+1 type, is a k+1 type, then this product is a k+1 type. It's a k+1 type. Okay, so what does it mean for a type to be a k+1 type? So by induction, that meant that its identity types are k types. So we must show then, so I'm recalling the definition of what it means to be a k+1 type, that for all FG, so for any terms in this type, that the identity type F equals G is a K type. But by function extensionality, this type is equivalent to the type of homotopies. This is equivalent to this type of homotopies, which I'll recall is this type. So this is by funnext. And one of the things that we've proven about K types is that they're closed under equivalence. So if you're equivalent to a K type, you're a K type. But by hypothesis, so, or I guess since B of X is assumed to be a K type, or sorry, K plus 1 type is a K plus 1 type, its identity type, so in particular, this F of X equals G of X, and B of X is a K type. Now, by our inductive hypothesis, we're assuming that products of families of K types are K types, and that's what we need. So by the inductive hypothesis, let me abbreviate that IH for inductive hypothesis. This type of homotopy is a K type, which is what we needed to show. So we're done. Great. So that's kind of wonderful as well. This base assumption that products of families of contractible types are contractible somehow generalizes automatically to all truncation levels. And we get some corollaries of this right away that are very cool. So firstly, so let B be a K type and let A be any type. So the claim is then the type of functions from A to B is a K type. So question for the chat, why is that true? Why is this type of functions a K type? I mean, and just to emphasize the statement, A is any type. So A could be a K plus 1 type, a proper K plus 1 type. A could be untruncated. It could be a type that has, non-trivial identifications in all levels. And yet, as soon as B is a K type, this type of functions is a K type. So why? That seems weird. Or does it seem weird? I don't know why. And also I'm saying this is a corollary. So I'm in fact not going to give a proof, though I'm asking you to give a proof. Great. I've seen one contribution. Anyone else want to give it a try? Maybe I will give a proof. Great. Yeah, there's in fact several different ways to think about this. This is wonderful. So I mean, firstly, this is just a special case of the previous result. This is a special case. So remember, function types are special cases of dependent function types where we're mapping into a constant type family, where all of the types B of X are just this constant type B of the previous theorem. So, kind of why is it true? Well, it's true for the same reason that the previous theorem is true. And it's really by function extensionality, saying that if we're interested in identifications between functions, it suffices to pointwise consider identifications in the codomain. So the fact that the codomain is the truncated type here is all that really matters. So great. Yes, everybody who's made a contribution had something valuable to add. So that's wonderful. So a special case of this result is that for any type A, the type, which is the negation of A. So this is a name of a type, but I'll recall what that type is. It's defined as the type of functions from A into the empty type is a proposition. Well, and why is that? So the empty type is always a proposition. And so just by the previous result, this function type then has level -1 as a proposition itself. So, I mean, that's kind of cool. So a type can be complex, but its negation is always a proposition. Okay, so that's one sort of application. There's some similar applications on your homework where you're asked, there's various types that we've been asserting are propositions, but we haven't really been able to prove that until this stage. And so maybe an added exercise is find other propositions, prove other types are propositions, prove other types are propositions. So that's a family of applications of the function extensionality axiom are that you can prove that various types that we've been claiming all along are propositions finally are propositions. So that's nice. But another family of applications proves equivalences, constructs equivalences between types that may or may not be propositions, and that's what I want to focus on right now. And the first one might be called the type theoretic principle of choice. Theoretic principle of choice. The name here might be a little bit controversial. I'm deliberately not calling this an axiom of choice because this is not something that corresponds most closely to the traditional set theoretical axiom of choice. And that's something that you could ask one of your TAs about, or maybe it'll come up in the future. But this is something that is just true in dependent type theory or in constructive mathematics. So this asserts the true fact, the fact that pi types distribute over sigma types. Distribute over sigma types. So the reason this doesn't connect so directly to the axiom of choice as is understood in sort of set-based mathematics is that sigma types are not a perfect analog of the existential quantifier. They provide a bit more information, namely the projection onto the first component. And using that information, we can state and prove the following. So the theorem, so for any family of types, so I'm going to start with a base type A, which could be in any context. So of course, I'm suppressing that. Then I have a family of types B over A. And then I have a family of type C over that pair. The map as follows. So we'll call this map choice, I suppose. And what it's going to do is, so if for all x and a, I guess I'll read it in a logical way to emphasize the analogy. So if for all x and a, there exists some y and b of x, so that c of x, y holds. So that's just a name for this type. Then it follows that there exists some function, this would be called the choice function, that is a function that for all x and a chooses some term of type b of x, so that then for any x and a, c is true of this pair of data x. So distributivity means kind of moving one past the other. So the pi to sigma and the sigma to pi is in this direction. And the statement is that this map, which you can sort of defined by, so I should define the map. So a choice would take as input some function, maybe h, and then its output will be a term of this sigma type. So it's going to be a pair, and for the first component, I'm just going to take lambda x PR1 h of x, and then in the second component, I'm going to take lambda x PR2 h of x. So this function is an equivalence. So the thing that we are going to prove with the weak function extensionality axiom with, and I think, sorry, with function extensionality, what we're going to prove is that this particular map is not just a logical equivalence. That's something we could have exhibited much earlier, but this map is actually an equivalence. And a thing I want to comment on is sort of distributivity of sigma over pi is something that we've seen already, in fact. So in the proof that weak function extensionality applied function extensionality, we had these maps, this section and this retraction. And the retraction was defined by taking a function valued in a sigma type and sort of separating it out into its two components. And that's exactly, that's a special case of what's going on with this general choice function here. Okay, so let's give a proof. So the first step of establishing an equivalence is a logical equivalence, and we can define the inverse map with no problem. The inverse map. So I'm just going to call it choice inverse because we're about to show that it is an inverse, but So this will be a map that goes the other way. So takes a choice function. So a term that for all x and a specifies an element of b of x, and then provides the data of proof that c of x, f of x holds. And then I'm going to convert that into a proof that for all x and a, there exists some y in b of x, so that c of x, y holds. Sorry, that's c of x, y holds. I'm going to define this by, so by sigma induction, it would suffice to define this on a pair. So given my f and my g, and I'm going to define this to be the function that for all x and a just returns that pair, f of x, g of x. So again, you might consider this with the section map that occurred in the proof that weak function extensionality implied function extensionality. So both of these are very, very canonical. All we're doing is sort of using our pairing and projection in kind of different orders. Okay, so the first homotopy, so to show that these maps are inverse equivalences, we're going to construct two homotopies. First homotopy, it suffices to give an identification So the first homotopy we're going to consider is when we do the choice inverse function first and then the choice function second. And since it's a homotopy, I'm going to evaluate it at a term here. And by sigma induction, I can assume that that term is a pair. So evaluate at FG. So I'm looking for an identification here where FG is exactly as above. But this left-hand side computes to the left-hand side computes to. So what I'm going to do is I'm just going to unpack the definitions. So this choice inverse of FG is definitionally equal to, so choice inverse of FG was the function lambda x dot f of x comma g of x. And then choice was defined by just kind of separating out. So I take lambda x dot f of x as the first component and lambda x dot g of x is the second component. So again, both of these are definitional equalities. That's the meaning of this extra dot above. And then by the eta rule for function types, this is just, and I don't know, maybe I'm using some structural rule involving pairing and definitional equalities. This reduces to just FG. So this homotopy is trivial. It's a, you could inhabit it by reflexivity. Okay, so for the second homotopy, and sorry, this is the direction that gave the section above. So this is we have not yet invoked function extensionality or weak function extensionality, which is why an argument of a very similar flavor was involved in the proof of the logical equivalence between those notions. So for the second homotopy, this is where we'll require a bit more. Homotopy, we require an identification. So here I'm going to do the choice inverse function second and the choice function first of H equals H. And again, we can compute the left-hand side. The left-hand side computes 2. So choice inverse of choice of H was defined to be, so the choice function took my H and paired together lambda x dot PR1 of H of x with lambda x dot PR2 of H of x. So the choice inverse function then sent this to lambda x, and then I'm pairing together the projections PR1 h of x, PR2 h of x. And so this is related to the question that Astra asked me a little while ago. So because we don't have an eta rule, I guess, for sigma types, we do not have a definitional equality. So a generic term of a sigma type need not be a pair. So we do not have a definitional equality relating h of x. So h of x is a term of type, the sigma type, sigma over y and b of x, c of x, y. So h of x is a term in the type sum over y in b of x, c x, y, and the pair. So in the absence of a rule like that, I cannot use reflexivity to inhabit reflexivity in the eta rule for function types to inhabit this type here, PR2 h of x. However, I do have an identification between them, and you know, that's kind of why we can get away without having an eta rule like this, is because we do have an identification between them. So let me try and remind you a little bit about that. However, we do have an identification. So these are both terms in this sigma type between them on account of our characterization of identity types of sigma types, because of our characterization of identity types of sigma types. So let me recall that. Maybe I'll just use some different notation. So if I have a sum over a type, so if I have two terms, let me call them P and Q, that belong in a sigma type. Let's say we're summing over some x of type D of x, or x of type D in E of x. Then the type of identifications in the sigma type is equivalent to, on the one hand, I could ask for an identification between PR1P and PR2, sorry, PR1Q. These are terms of type D. Or I could transport in the family D the data of such an identification alpha, and then PR2P to PR2Q. So this is in the family D of PR2, so PR1Q. And so we had an equivalence between identity types and sigma types that looked like this. And the point is, if I'm trying to identify my term h of x and this pair over on this right-hand side, then what I'm looking for is identifications involving the projection of h of x. So the first projection of h of x and the second projection of h of x. So in our case, I would have a pair which is like a Riehl and a Riehl, and I can map it back under this equivalence to get the identification that we want. So get our desired identification thing. Okay, so what we have then, so this gives us, so Egbert gives a name to all of this data, so I'll just use the name here so you can look it up if you want. So EQ pair is the name of the inverse equivalence here, and I could apply it to this pair of Riehls, and I have one of these for all x. So this is giving me a homotopy between choice inverse of choice of H. So I wanted an identification between this and H, but by function extensionality, which is what we're using now, that suffices to give an identification, and that's what we need. So fun X makes this an identification, and thus a homotopy, and then gives a homotopy. So we were trying to prove that choice inverse and choice are homotopy inverses. And we get that homotopy from having an identification here, which we get from function extensionality. So that's the end of the proof of the equivalence. Great. So there are a lot of results in this family, and many of them would be described under the moniker universal properties. So there's some examples on your homework, but I want to give you one as well. And this will return now to the discussion that we had on the beginning. So in general, universal properties characterize maps out of or into a given type. So this is a term that comes from category theory. In this context, we're going to have universal properties associated to inductive type families, and these will characterize maps out of inductive type families. Most of that, the data of that characterization we've had long ago, kind of the final missing piece is what's given by the function extensionality axiom, which is what we have now. So the first example I want to give is the universal property of sigma types. And this can be understood as a generalization of the motivating example that we discussed above. So hopefully this will look a little bit familiar. It's a generalization where things are kind of maximally dependent on another. So let B be a type family over A, and let C be a type family over the sigma type. So then the map, where I'm going to look at sections of this type family C. So that'll be maps out of an arbitrary term in the sigma type and into C. I'm going to compare that with maps defined just in the case of a pair. So we'll take an X and A, and a Y and B of X into C of XY. And this map is EV pair, same EV pair we've seen above, given by F maps to, for all X, for all Y, we just apply F to XY. So this map is an equivalence. Okay, so the non-dependent case of this, when B does not actually depend on A, when it's constant over A, this sigma type is just the product type A times B. And when C is constant over that, so it doesn't actually depend on that, this function type here is the type of maps from A times B into C, whereas this type is the type of maps from A into the type of maps from B into C. So this is exactly the same setting we considered above, but now using full dependence because it's true at this level. So let's recall the part of how far we had gotten in the proof, and then we'll finally be able to complete it. So the inverse map to this EV pair, so this EV pair is really like a restriction along the constructors in this inductive type family. The inverse map is the induction principle. So here I'm going to call end sigma as opposed to end times because we have the full sigma type. And what it is given to you as is just a map like this. So in part of the definition of sigma types, we're provided with the data of a map. This is from the elimination rule or the induction principle. And then we're also provided with a computation rule, which is used to construct one of the two, or to exhibit this as a section of EV pair. So by the computation rules for sigma and pi types, we have a homotopy. This is a homotopy that relates EV pair after end sigma with the identity. And you could unravel this and it'll be the same computation that we've seen above. So the summary, again, is that the induction principle and the computation rules show that this induction map is a section of evaluation of the constructors, but function extensionality is used to complete the part of the proof where we got stuck. Function extensionality provides the other homotopy. So what we still require is a homotopy between the composite the other way around. So in sigma, ev pair, and identity. So let's do that. So for this other composite, so this requires an identification, So I'm going to introduce a term F, like in the statement of this theorem, for all F, which is a section of the type family C. So that's a term that would take Z in here, C of Z, and that require an identification between ind sigma. So ev pair was the function that took a X and a Y and produced an FXY. So in sigma of ev pair of F is this expression, and I require an identification here. But by funnext, this is an identity type in a function type. So it suffices to show, instead give a homotopy. So for all Z in here, it would suffice to give an identification between in sigma of this function and a Y fxy applied to Z and f of Z. So in other words, by funx, this is equivalent to the type of homotopy. So it suffices to give an identification in here. And now by sigma induction, I can reduce to the case where Z is a pair. By sigma induction, we can reduce to the case where Z is a pair. Case of pair AB in the sigma type. And in that case, both sides reduced definitionally are definitionally equal to just F of AB, definitionally FAB. So I can use reflexivity, pass it through sigma induction, pass it through funx, and that gives me the data that I need of this final case. Great. Okay, good. And a corollary is the currying uncurrying equivalence that we sought above, implemented by the data that we described there. So I won't say too much about it now, but great. So in the last few minutes, I want to give one more example in this family. This will be the universal property of identity types. And what I want to try and explain is the connection between this and something in category theory called the Uneeda lemma. So unfortunately, I don't believe this explanation will make any sense if you've not heard of the Uneeda lemma. So if that's you, that's okay. And you should ask the TAs to say a bit more. Identity types. Okay, so, right. So actually the Uneeda lemma connects most directly to a special case of the universal property of identity types. So I'll start there. I guess I can say the based identity type for some type A and some term A and A is a family lambda x dot A equals x. So that's a family of types over A valued in the universe. So let's consider another family of the same form. So consider now an arbitrary type family from A into the universe. So on the one hand, what does this be? It's a function. So B is a function. B maps a term X in A to a type B of X a term in the universe is just the way to say a type. And there's a sense in which B can be understood as something like a functor. It's functorial in paths in A. So B also maps a path. So if I'm given a path P from X equals Y, I guess the thing that's probably most familiar is we have this transport function. So transport in the family P, B over the family, in the family B, the path P gives the data of a function from B of X to B of Y. And so that's sort of the sense in which B is functorial. So it takes a term of type A and produces a type, and a path in A and produces a function. Okay, so from that point of view, this identity type family, so that was this one above lambda x dot a equals x, is also something of the form. So this could also be a functor, valued in the type universe, indexed by types. And in category theory, once we have notions of functors, it's natural to reason about maps between them, which take the form of natural transformations. And what is the natural transformations? So natural transformation provides for each term a map. So a natural transformation. So this is using language that is familiar from category theory. So I'm putting it in quotes from the identity type family. Into my arbitrary functor B is a term of type. In other words, the type of natural transformations is the type that I'm about to define. So it would provide the data for each X in A of a map from this type to this type. Now, ordinarily, one would, in addition, have to check some sort of naturality condition, but in that case, this comes for free. So, which is something that you definitely need to use a pen and paper to figure out. So all of this is to explain why the following theorem might be called the innate lemma for folks who know about the innate lemma. And what is the innate lemma? So the innate lemma asserts an equivalence between natural transformations and much smaller data. So the following map is an equivalence. So the innate lemma says that if you have natural transformations out of a representable functor, that's the role that's being played by this identity type family, representable at the term A. So this here is this type of natural transformations. And that's equivalent to the data of a single term in a single fiber of B, namely the fiber over the special A. And the way that you would extract that single term from a natural transformation is evaluating at the identity of A, or the way we call that here is REFL A. So evaluation at reflexivity of A defines a map in this direction. So given a term of this type, you could plug in A there and plug in REFL A there. Maybe this is evaluation at A comma REFL A to get a term of this type. And so that is the assertion of the innate lemma. So the full universal property of identity types is actually stronger than this. It allows this type family B to depend not only on A, but also an identification in A. So the full universal property of identity types is stronger. And now I'll state that. And this is where you should tune back in if this category theory language is just abstract nonsense to you. So the full universal property of identity types is stronger, and I'll state it and prove it now. So this theorem is, again, a special case that's a little bit less dependent than the fully dependent case, which is the thing that will actually be sort of easier to prove. So I'll call this theorem dependent innate lemma. slash universal property of identity types. So pick your favorite name. Both names are equally descriptive of identity types. And here's the statement. So let A be a type. Let little a be a term in type A, and consider a type family B that BXP, that's a P, a family over a term of type A and an identification between A and X. Then the map of Riehl, so evaluation at reflexivity, which would take a section of this type family, A equals X, B XP, and return just a term in the fiber BA Riehl A is an equivalence. Okay, and this is exactly the same. So this by now, so the UNADA thing is probably unfamiliar unless you've read some quite advanced research papers in category theory. This version of the universal property might be more familiar because it's very deeply analogous to the universal property that we just proved for sigma types. And indeed, the universal property of all inductive types has this form. The domain of this, so this evaluation map is an evaluation at the constructors of the inductive type family. So for identity types, those are just the reflexivity terms. The domain is the type of sections of an arbitrary family of types over the inductive type family. The codomain is just sort of whatever it has to be. And this assertion is the equivalence. The proof is going to be very, very familiar as well. So I'll quickly give it and then we can wrap up. So the inverse map is given by the induction principle. So the inverse map is, so in the case of the identity type family, we call this path induction. The way this is set up now is this one-sided path induction. So what path induction says is that if I had a term in this single type, I could construct a dependent function. Or in other words, to construct a dependent function, it suffices to give an image of the reflexivity paths. That's the form that we use, path induction. And this is a section by the computation rule. Section by the computation rule. This would be much simpler to spell out in full than the cases we've seen above, so I won't say anything more. But the computation rule says if you've defined something by path induction and then you evaluate it at reflexivity, you recover the data that you defined the thing from, or identity types. Okay, so what we require then is one more homotopy. That's always the case. So for the other homotopy, this is the hardest part. So the other homotopy in this case, I need a homotopy between what happens if I do the path induction thing second and the evaluation at the Riehl thing first. I need a homotopy from that to the identity. So I'm going to consider a term in the domain. So that's an F, which is a function that takes an X and A and an identification P and produces a term of type PXP. So we require an identification then between path in A of F evaluated at this A Riehl A. So that's what ev Riehl of F does. I require an identification like this. Now these are both terms, these are both names of functions in this dependent function type. So constructing an identification between functions is a priori hard, but now we have function extensionality. And here I'm going to apply this function extensionality twice. Twice because we have two product types here. We have an iterated product type. It suffices to show. So rather than construct an identification between functions, I could pick an X and pick a P. And then for all X in A and for all P from A to X, I need to identify path in A of F A Riehl A. That was the name of my function, but now I'm evaluating that function at my pair XP. And I need to identify that with F evaluated at the pair XP. But now I can use the computation rule for path induction. So, sorry, I don't get to use the computation rule. I use the induction principle first. So by path induction, I mean, my goal right now is to inhabit a dependent function type mapping out of an arbitrary X and an arbitrary P. That seems hard, but by path induction, it suffices to show. So I can reduce this to the case of where my P is reflexivity at A and X is equal to A. So in other words, all I need to do is give an identification between path induction of A, of F, of A, refl A, that function now just evaluated at A, refl A, and I need to identify that with F, A, refl A, but this holds definitionally. This holds definitionally by the computation rule for path induction. Definitionally by the computation rule for this path induction term that we've used already. Definitionally by computation rules. Okay, so that's the end of that universal property. So what we've seen so far with function extensionality, which is the axiom that we've added today, we have a characterization of essentially all of the types that we have considered. I guess in the hot track, we haven't really discussed higher inductive types, so we don't have characterizations yet for those. But the one type that we are very conspicuously missing a characterization of its identity types is the universe, and that is what the univalence axiom is about. I know Egbert has a lot of things that he will tell you about that, and so I will wrap it up here. Thanks so much. This was fun.
Thank you very much for the 3 lectures, Emily. They were excellent.